Dan Olds here. It's another Winter Classic Invitational Studio Update show. And this is a big one. This is the Oak Ridge module. We're talking to the mentors, and this is the very first time in any student cluster competition where the students have dealt with not only quantum computing, but run on a quantum machine for at least part of the challenge. And we're going to get into that. But first, let's meet the mentor teams. If you could just introduce yourselves. And let's start with Michael.
Hey everybody, I'm Michael Sandoval. I'm an HPC engineer here at Oak Ridge and part of the user assistance team. I deal with quantum computing on a day-to-day basis because I manage our quantum computing user hubs for our quantum computing user program.
You're the quantum driven man then. Your
To a
life is
degree,
quantum.
it
Okay.
is.
Very nice. Very nice. Murali, let's talk to you.
Hey everybody, my name is Murali. I'm a computational scientist at OLCF. I work in a sister group as where Michael works at. My work is mostly around analyzing and modeling, excuse me, turbulent flows.
Little
Particularly,
CFD, eh?
yeah. So mostly with CFD, looking at massive turbulence simulations and trying to understand what's going on using tools like machine learning. And now with quantum computing, different algorithms can be accelerate these simulations or analyzing them. So
We're going to be hearing more and more about that in the next few minutes. Dan Dietz, probably a familiar face to some of you of the millions of people that are following this. He's been involved on the Oak Ridge side with this competition from early days.
Yeah, hey everyone, I'm Dan Dietz. I'm an HPC engineer with Oak Ridge. I work on our systems acceptance and user environment group, so we get to do testing all the new systems that we're bringing in and making sure that everything's working the way it should be. We also manage all the user software that all of our users are using on our systems.
Very good, very good. Yeah, you might know a little something about LinPack, I would imagine.
Yeah, we use that
A
in
little
some of our
bit.
yeah.
Some other stuff, sure. So Callian, am I pronouncing that right? Oh, you're on mute
You're
still.
muted.
Pretty
So
close.
Callian, close. Okay,
Pretty
I'll
close.
accept that.
Pretty close. So I'm Kalyan. I work in the same group as Murali does. I work in NCCS. My background is essentially turbulent combustion, and I use that. I use tools like HPC, and we use the largest computer here, that's Frontier, to run some of the biggest calculations ever, and I help teams with that. And recently, we have been working a lot on quantum computing and extending that to do some tough problems with computational fluid dynamics. And that brings us to this student competition.
Yes, where they got a taste of that. Let's talk to you for a minute, Chow. How are you?
Yes, hi. My name is Chow. I'm a postdoc in Oak Ridge. Currently, I'm working on quantum algorithms to accelerate quantum fluid dynamics problems. And I also try to benchmark the algorithm using quantum computers with performance and accuracy and stuff.
Very nice, very nice. And I see that Veronica has snuck in, another familiar face. How are you, Veronica?
Hello, sorry I'm late.
That's
I'm
okay.
from another building. But yeah, my name is, it's great to see you too. My name is Veronica Melessa Vergara. I'm the section head for HPC operations here at the National Center for Computational Sciences. And I'm a very big supporter of the competition, not just the Winter Classic, but I've been involved in the student cluster competition at SC too. But this one is near and dear to my heart because of
This is the best one, isn't it really?
participation.
This is the best one.
I really
on.
admire because it like has more accessibility because it's virtual and you're reaching out to communities that we always want to reach out to, and I think it's a really good way to bring in new people and maintain a broadened participation of people in HPC. So thank
And they're hungry. They are not phoning it in. So great. And the great thing about Oak Ridge is you're always throwing something new and unique at them, and none more than this one. I mean, this is groundbreaking. Who wants to take the ball and explain a bit of what you had them do and how you had them do it?
Yeah, I can give a broad introduction. We essentially gave the students to explore this particular algorithm in quantum computing called quantum linear systems algorithm, which, as the name sounds, is to solve linear system of equations. So you talked about LINPACK, Dan.
Yeah, it looked a little linear algebra-y to me when I looked at the briefing stuff.
Absolutely. So you can see it as a counterpart on the quantum side. And specifically, we requested the students to tackle some sample problems, some sample matrix equations, and also to solve a sample fluid dynamics problem that we've been trying to tackle in our research at the center as well. So the uniqueness of this, one of the additional uniqueness, as Dan mentioned, was apart from enabling the students to run these codes that we have on Frontier's testbed system, we also enabled them to run these circuits on an actual quantum hardware, which was IQM's quantum hardware. This was a huge effort from our side too. Maybe I can hand it over to Michael to talk about the process that was involved. A huge effort from Michael to get that enabled.
This was a big lift. Tell us about it, Michael.
Yeah. So for those that don't know, here at Oak Ridge, we have a program called the Quantum Computing User Program, also known as QCUP. And we partner with cloud vendors who offer actual quantum machines on their end. And we essentially take in proposals from prospective users, evaluate, like, does this seem, is this publishable? It goes through a review process just like our classical HPC proposals do. We can offer them quantum computing resources. In this case, one of our partners is IQM, and they are one of four. We partner with IBM, Quantinuum, IonQ, and IQM. A lot of I's in there, a lot of Q's. But part of the reason why this was, I guess, a great effort on our side is because this is the first time we were doing this. We've never actually been able to or tried offering either a training event or a cluster competition that gives users or even students access to these resources to come and try things out and learn quantum computing. And we wanted to enable that sort of building up of the workforce and teach students who may not have an opportunity elsewhere to ever do this, to sort of get them in and, hey, it's a cool subject and maybe you might be interested in it. And now it's officially in our scope within the QCUP program to develop the workforce in the future. So this is just opening the door to much more possibilities in the future to do something like this again.
Well, and it's amazing that you were able to hook them up with running on a quantum system, but running on the Frontier clone, the small one, sort of like how Ascend was with Summit. That's a big step forward too.
Yeah, exactly. And Frontier up until recently was the fastest supercomputer in the whole world, had over 9,000 nodes, and it hit the exaflop barrier and things like that. And Odo is a lot smaller than that. It's only 30 nodes, but it's still the same architecture as Frontier. Still pretty fast, pretty dang fast.
Pretty sporty.
And we're able to get some good problems done, not only for students here, but those elsewhere that are able to use Odo for sure.
Yeah, it's a great training resource. Absolutely. So trying to figure out where to start on this, but I guess let's start at the beginning, well, actually, no, let's separate things a little bit. What problems were they running on Odo, and what were they doing on the quantum system? Whoever wants to take that.
All right.
Rally steps up. Good.
So yeah, I can give a broad idea of the different tasks.
Yeah.
So mainly there were 3 tasks involved. The first 2 tasks were designed for the students to get a little bit of their feet wet on like what is this code about, what are they trying to do, what are the different parameters involved, how can they run on these different systems, right? On the Frontier clone, Odo, or on the real hardware. So those were the 2 tasks. I'll go on to the details a little bit. The third task was to use whatever they learned on the previous 2 tasks and then apply it to a practical problem. The practical problem that we chose was this canonical fluid dynamics problem. That is the flow between 2 plates. If they're really close to each other, you get a very nice ideal flow. It's kind of like a model, but you can, and there's solutions to it that you can easily compute. But then it has practical applications like in microchannels or in porous flow or in capillary flow and things like that. So that problem essentially is solving a system of linear equations.
Okay.
You learn how to tackle this quantum linear systems algorithm, try to run it on different systems, and then apply it to a practical problem. So those were the 3 tasks. And on the first 2 tasks, to dial it down, first one was essentially to understand what this code was and look at one of the main parameters, which is the number of shots involved. So when you create a circuit and when you want to run it on a quantum hardware, to get a good statistical result out, you need to run the circuit multiple times. And you collect the probabilities of your results, and you get a good statistically good result. Right. So what was this influence of the number of times you run the circuit on the hardware? Are there any uncertainties involved depending upon how many times you run this? So
and that's running it unchanged. You're not changing variables or anything. You're just running it multiple times. This is all probability based, right?
Absolutely. It's the same circuit, the same problem, but what happens if you run it multiple times? And again, if you run it in a different experiment completely, you run it, say, 100 times, get the results out of the probability. But what happens, say, in a later time, you do the same experiment again 100 times to get the same probability distributions.
I mean, it should settle down to
essentially as you
right? Yeah.
increase the number of you get a more statistically good answer. But then depending upon when do you run, there is some uncertainty on your final accuracy. So concepts like convergence of your solution and what is the uncertainty involved, those were the main part of the task one. Kalyan, did you have a...
Yes, so just
Please.
add to what Murli was saying. The tasks were also set such a way for the students because they are not used to quantum computing. I mean, that's what we assumed. And quantum computing is different from classical computing. In classical computing, we generally expect you run a software to that accuracy for that particular machine, for you to get the same answer every time you run it. That's kind of, you have to. Now with quantum computing, the whole concept for them to understand is there is a measurement, it is a probabilistic thing, and the tasks that are set are in such a way for them to slowly come from that mindset of classical computing to quantum. And it's not a trivial thing. We are really happy the teams were able to execute what they did, because it takes a bit of time for you to wrap yourself around to think in a different way. The algorithms itself are different that's the reason they are different for classical versus quantum computing. How you evaluate on qubits, how do you measure and get your output is different. So the way the tasks are set is such a way. Why we set with a very simple thing was that for them to understand why do you even need like shots, and that you don't get like an answer right away. There is a convergence to that. And for you to determine how many times you have to run something to get a statistically significant answer. And now
And that's the
number,
convergence.
that's the convergence criteria.
Okay.
Now,
Why don't you
once
just
they-
call it statistically? Why don't you just call it an average? Just kidding. That's always confused me when I've tried to wrap my head around quantum, all the new terminology, but it's
Yes.
good.
So once, I mean, lot of them got that from the evaluations. We could see that they could understand why they could need that shots, and that number was key for the other tasks. And from there on, they had other things to look at when you are running on different systems, like for what we call a simulator, emulator, as well as the actual hardware. You have different fidelity, that is accuracy in your answer, and so that is something that they investigated next. And then based on these two things, that okay, now you have to collect it like a statistics as well as look at what is the fidelity on different systems. Then they went on to apply it for a much more like a close to a practical problem, like Murali said, a Healy shock case. And that's actually also tough, because a lot of these students don't have exposure to fluid dynamics, much less computational fluid dynamics.
Yeah.
So the team did an excellent job of giving them that background of fluid dynamics as well, and to all this sequence of things. And Michael did a great job of giving that resources too, and explaining them how to execute on these machines. And there are several things here that actually make it a challenging task, because executing on Frontier itself for folk who run it for the first time takes some time. And for them to learn that, as well as executing on quantum hardware, while understanding that there is difference in going through both classical and quantum systems, and then coming to a computational fluid dynamics problem and actually solving that and getting something that we are looking for. I was amazed at some of the teams that what they achieved.
Oh, that's incredible. I guess let's walk through how the students progressed throughout that week. I mean, it's not much time. They're still full-time students. They all still have jobs and stuff too. Did you see the most successful teams getting started early on this?
That's a good question. We definitely saw a trend. We monitored both jobs on the classical side on Odo and on IQM side as well. And near the beginning of the week, we saw maybe 10 to 20 jobs. Well, once we started to get into Thursday, number spiked really high to near hundreds of jobs. And then on Friday, it was a big delta function of even more hundreds of jobs, closing to 1,000 on Odo. And on the IQM, and they were reaching hundreds of jobs, and that was only one part of the task, right, of the three. So we were very happy by the end of things to see the students run over 1,000 jobs on Odo and nearing 300 to 400 jobs on IQM, which is comparable to a user running a workflow for the entire year. So they ran a total of jobs in the span of a week that normally we see on order of months to a year on the quantum side. And we did see that the folks starting early did seem to perform better, because then they had time to wrap their head around things and then ask us questions if need be, right? To sort of get into that mindset. Yep.
So what sort of questions did you see? A lot of questions, first of all. And were they, this is hard, we don't get it at all, or were they more focused and specific?
I'll let you go, Murali.
No, please go ahead, Michael.
Of the questions that I saw, a lot of them were revolved around like the uncertainty of running the same code over and over again. So they're trying to get into the mindset of, oh, if I literally just press go twice, how did this affect things and why does the answer sort of look different for certain backends? And so it's sort of a lot of those questions were what actually is uncertainty at the same time, and sort of guiding them to be like, oh, this is what we mean by uncertainty for this case of the inherent randomness of the script. Murali, you may have seen more questions as well.
Yeah, and there were some more questions regarding like navigating the code as such. We gave them a sample script. You just have to use that script, press enter, it will do stuff. But then as you progress towards the task, there's a little bit of effort into going into the code and, you know, looking at what's actually happening, at least a little bit. What are the solutions being saved? How can I use that to, you know, create this uncertainty plot and things like that? So there are a few questions regarding the codes as well, the plotting routines. It was not more, we didn't get this broad question of, oh my God, this is so hard. They were more focused, and we were pretty happy with that. That's showing that the students are on target. They're getting these concepts and navigating through these different processes. Yeah, one thing I would like to add is I personally thought that, and I think we are all on the same page, like maybe the students might have had, if there was like one more week for them, it would have, you know, enabled them better towards navigating through this new thing.
Yeah. This was that big, and actually I should have been in contact with you because we had some mentor organization turmoil with some that couldn't do it at the last minute. We could have done 2 weeks. We could have done that.
Even what we saw, I forgot about the plotting routines. That was a lot of questions as well, Murali. Yeah, good point. Even if it was just an extra week for them to figure out how to plot in Python, we had some guides on that we have around from our HPC crash course that we do that we were able to point them to. So we had the material to point them to get them started. And of course, Murali pre-made Jupyter notebooks for them to have like a template.
That's helpful.
I'm glad that we were able to point them to all that. But yeah, I think even for teams that just needed to make the plots but ran out of time or whatever, it would have made sure that they like, oh, I'm going to understand Python plotting too, as well as all of this quantum computing stuff, which perhaps for some teams it was new to both of those things, right?
Yeah, I would imagine that it was. I mean, and we should talk earlier next year and see what other wild thing you come up with that we can make sure there's appropriate time, because this would have been a great one for you know, an extended challenge. It certainly would have been useful to them, and they got a lot out of it. And this is definitely, as I've been telling them, this alone is resume worthy.
Oh, definitely. I mean, I can't imagine, like, even as a student myself going up, I know quantum is still fairly new and fairly growing, but not a lot of places, one, have the user program to enable this, but two, have, you know, partnered up with a quantum vendor to even have the potential of offering any resources.
I mean, that's a vanishingly small, and this is experience that, you know, undergrads in large major universities, they don't have this shot. They're not going to get this out of their regular computer science major classroom stuff.
Right. The cool thing though is a lot of the software, and part of which we used, have simulators built into it. So although if students are watching this somewhere else that want to get started or want to play around with it, they could, you know, download the open source software and play around locally on their own machines if they have them, to run quantum simulators. And it's not an actual machine, but at least get them in the door and the mindset to pursuing that path later in their careers, or maybe they want to do a research project or something like that. It would be a nice start.
Well, this was an incredible effort, and you pulled it off in a fairly short amount of time. I mean, you sort of had this idea, right? I mean, a couple of months before the competition, maybe?
I think that's a bit generous.
It's shorter than that. Shorter than that.
Shorter than that. Okay.
Yeah.
Okay.
Yeah. It it was definitely shorter, but like Michael, Morelli, Dan, Gallian, and Chow, they did awesome because I mean, usually, like you said, we were trying to figure out like what's new so we don't repeat the same application or even the same domain as last time. And it was like, well, we've been doing a lot more conversations on the quantum, at least that's an area that obviously is exploding. And we're like, how hard would it be to make something that an undergraduate that's not taking quantum mechanics or anything even remotely close could do something digestible as like maybe as a thought. But then Michael and Kalyan and everyone ran with it and they were like, sure, we can make something. And
Yeah,
it
we can
wasn't
do
a ton of
that.
time, but they did such an awesome job because
Oh,
it
yeah.
is definitely hard to digest material. And they made it so that it's something that they could, one, understand what's going on, but also be able to do stuff themselves and learn a little bit about it. And quantum is an area that is HPC is already hard to recruit workforce. Like quantum is even worse. So like starting earlier and
Yeah.
giving access is definitely something we're very interested in.
Fantastic. And I mean, wow. This was the most complex and advanced task our students have ever done. And I want to say this is experiences that no other students have had in any of these competitions. And thank you so much for it and for putting in so much time and effort. And I'm looking at the detailed results. This was just amazing. Um, and the students got so much out of it. I'm wondering, how do you top this for next year? Or do you just retire now and we'll never hear from you again? But you've always come back with something bigger and deeper. How do you top this? Any thoughts yet?
That's a great
You have
question.
time. You have time.
Yeah,
We do
start
have
to
time.
think now. Like start to think about it now instead of when we did this year. But yeah.
Well, that will definitely be something to look forward to. And I will absolutely reach out earlier in case you do need extra time because, well, I sort of own this thing, so I can figure that out and make plenty of room for you if you need it because it's certainly paying off for the students. And actually, one thing I may or may not have shared with all of you, but I've done some research in talking to the students from past competitions, see what they got out of it. And close to 75% of them said that before this competition, they didn't know that HPC was a thing. Just didn't know. After the competition, and it's like 3 months or more of work for them, close to 75% want to make their career in it after the experience. And that comes, straight to the work that you folks and the other mentors do to show them how intriguing and crucial this segment of computing is. And it's working. So
Yeah.
yeah.
And from the quantum side of things, it's not
Mhm.
going anywhere, right? I like the quote that is always used is that nature is inherently quantum mechanical, or I butchered that quote probably, but it's something of that effect, right? But and part of what we're exploring here at Oak Ridge is like we have our supercomputers and we're very well versed on that side of things. It's like, okay, how do we bridge the gap not only between our two communities of the quantum end and the classical end, but how do we, from a technological perspective, leverage both sides, right? We want to maybe like instead of a GPU where it can accelerate your code for certain portions of it, maybe a QPU, a quantum computer can accelerate certain parts of the code with certain algorithms and not completely abandon one thing or the other, but
No,
help integrate those two together to create, I guess, a more well-rounded ecosystem is part
I
of
mean,
our goal here.
I think it's coming. And again, a lot of that pioneering work is what you're doing, and you've brought our students into that world. So thank you so very much for doing that.
Yeah,
Oh,
and it's been a pleasure to and very gratifying to offer this to students that might not be able to view it anywhere else, but also helps us keep an eye on what the community is interested in. So that's part of the QCup program's mission is like we want to evaluate the technology, and like our 4 different vendors may offer something different to the table, sure, but it also helps us keep an eye on what the users care about, what scientific problems are interesting, especially for quantum computing, what students are interested in. It really covers the whole area of across the country, really, of what folks may care about in the quantum computing game and at our center, of course.
Absolutely. Well, you've done it again. So rest up for a few months, maybe a few weeks, and then think about what you can bring to the table next year. Because you keep topping yourselves. Thank you, everybody at Oak Ridge, everybody on the call, and everybody else who helped make this possible. Really appreciate it as always. So thank you. Take some time off. Take the next couple of weeks off. All of you just go home, and then we'll start talking about next year.
Sounds good.
Thank you. Bye-bye.
Good, thank you.
Thank you.